Hello and Assalamu alaikum. Today we'll be presenting the project titled The Development of a Cart Mounted Inverted Pendulum. My name is Adil Ali Khan and my group partners are Abdullah, Siddiqui and Sarwan Shah. We hope that by the end of this video we will have convinced you why our proposed project is worth pursuing. Our key objectives are twofold. The first objective behind our project is to develop a cart-mounted inverted pendulum test bench for utilization in the control lab. The purpose being to enrich the understanding and exposure of students by allowing them to conduct experiments on our platform. Secondly, we ourselves intend to carry out research on the test bench. This will involve investigating the use of computer vision as a feedback mechanism compared to traditional encoders and tackling issues around latency minimization by exploring the potential of using FPGAs for image processing.
To establish the need for a cost-effective test bench, our survey of existing solutions revealed to us the availability of some industry-grade inverted pendulum equipment in the market. However, with all of these came a hefty price tag. So we reached out to some of the leading solution providers such as Quanzer and Liebholz for quotations. What you see in front of you is a Quanzer inverted pendulum that is priced at $6,000. And over here we have a Liebholz inverted pendulum that is priced at a staggering $15,000. We believe these quotations themselves reflect a strong need to develop a local solution, then purchase a commercial one. As for the research tangent to our project, the idea of using computer vision as a feedback mechanism for control is not entirely unique, as seen in these papers by Lewis, Harris, and Ingram, which were also a part of our initial motivation for this project. The vision-based research conducted so far in popular literature has mostly been limited to low-level inverted pendulum configurations, and the use of vision-based feedback along with FPGAs has not been implemented on a cart-mounted inverted pendulum setup to the best of our knowledge. And this is the domain we plan on exploring.
And now let's talk about our deliverables, that is, i.e. what we are hoping to have accomplished by the end of this project. The first step, of course, is the construction of the test bench that will include a mechanical structure for the track, the cart on the track, and the pendulum mounted on the cart. You can see a visual representation of these modules in the block diagram in front of you. Similarly, we'll be including an efficient mechanism for the movement of the cart, a locomotive module consisting of a belt-in gear mechanism or a rack and pinion mechanism. Another component is a feedback generation, which will be conducted using encoders or a camera and will be interfaced with our data acquisition module. We will also be utilizing FPGAs for image processing, and this is also our primary research motivation, i.e. investigating the feasibility of FPGAs for image processing, their latency minimization, as well as contrasting the use of FPGA with a conventional PC or a GPU for image processing efficiency. We will also be including firmware in our project to provide low-level control of the system hardware such that it's easily usable by a student or even a layman. A graphical user interface for student engagement will be designed using MATLAB or LabVIEW. What you see in front of you is the GUI Quanzer has designed for its inverted pendulum setup. We will also be testing the functionality of the system by testing it for stabilization on a single inverted pendulum configuration to begin with. And lastly, we'll be designing a lab manual incorporating a mathematical model, related parameters, and guidelines on how to design a controller which ensures that our platform can easily be used by any student. And this is the block diagram where it all comes together and where you can clearly see the relationships between all the modules that we just talked about in the deliverables. We have the power module, which is supplying the actuator module, which is controlling the locomotive module, which in turn is connected with the pendulum, the feedback generation module, and the data acquisition module, all of it interconnected with the controller, the firmware, and the computer comprising the user end module.
Our project. Now let's take a look at the key features that make our solution desirable and unique. Firstly, ours is a cost-effective solution as compared to the existing products already in the market as outlined previously. Scalability is also an important feature of our solution. Our platform will allow easy extension from a single inverted pendulum configuration to a more complex double and triple configurations. Furthermore, one advantage of building this solution ourselves is that it will be open source. in the sense that our students will be interacting with our platform and not only learn to implement a control algorithm but can also be involved in other parts of the system, for example, how actuation, sensing, or noise filtering is being accomplished. Lastly, our setup will help open avenues of research in the inverted pendulum domain for ourselves and for the future students who can also utilize our test bench for further research, such as exploring different control methodologies. Therefore, by the end of our capstone, we plan to have created a mechanical structure and a software interface, designed a lab manual, tested out its functionality, and made some significant contributions to vision-based research in the field. So let us now conclude with this video of a single pendulum desperately trying to reach its inverted state. Thank you for your time, stay safe and take care.